Now we'd like to determine how to combine impedances that might be in series or parallel. Because Kirchhoff's voltage law and Kirchhoff's current law apply, we suspect that impedances in series will add, just like resistors in series, and we suspect that impedances in parallel will be the inverse of the sum of the inverses, just like resistors. But before jumping to that conclusion, let's take a look at these three impedances in series where we have a resistor in series with a capacitor in series with an inductor driven by a current. If we were to have an equivalent impedance ZEQ, then the voltage across the series connection of these must be the same if they're driven by the same current. And we can figure out what that voltage is, Vs. Vs will simply be equal to R times our current plus our current divided by J omega C plus J omega L times our current. On the other hand, for the equivalent circuit, Vs should be equal to our equivalent impedance times the source current. We know that the two source voltages should be equal if the impedances are equal, so I can equate these two. I'll group my terms together, R plus 1 over J omega C plus J omega L, all times my current should be equal to my equivalent impedance, Z equivalent times I. For this relationship to hold for any current, any phasor current that is, my equivalent impedance, Z equivalent for series devices, should be simply equal to then the sum of the individual impedances from I equals 1 to N for however many I might have in series. And so you can see that the series equivalent is simply the sum, or it's just like resistors. The only difference now is instead of a simple algebraic sum, we're using complex numbers. Moving on to look at impedances in parallel, we'd now like to determine the equivalent impedance of a resistor, an inductor, and a capacitor all in parallel. Again, we suspect that it's going to behave just like resistors in parallel, but for these two to be the same, if I apply the same voltage across them, the current flowing from the source, Is, must be the same in both cases. In the first case, we can see that Is will be equal to the sum of the current down through the resistor, IR, plus the current down through the inductor, IL, plus the current down through the capacitor, where the current down through the resistor will be equal to the voltage divided by the resistance, while the current through the inductor will be the voltage divided by J omega L, and the current through the capacitor will be the voltage divided by 1 over J omega C. On the other hand, the current Is in our equivalent circuit will simply be equal to the voltage divided by our equivalent impedance. We can equate these two, and we can now write that the voltage multiplied by 1 over R plus 1 over J omega L plus J omega C must be equal to the voltage over the equivalent impedance. For this to hold for any voltage, Z equivalent in parallel must be equal to the inverse of the sum of the inverses of the individual impedances. And this, as you can see, again, is just like resistors. Except, of course, now we're not just adding up real numbers, we have to add complex numbers. Now you'll notice that in general, my impedance, Z, will consist of a real part, known as the resistance, plus an imaginary part, Jx, where R is real, and that's our resistance. The imaginary part, X, is known as the reactance. In some cases, it's more desirable to think about the inverse of the impedance, and we call that the admittance and give it the symbol Y, and Y will be equal to 1 over Z, and that's equal to our admittance. The admittance Y has a real component, which we denote by the letter G, plus it'll have an imaginary component, which we denote by the letter B, where G, as you might suspect, is our conductance, and B is our susceptance. The units of resistance and reactance are given in ohms, and the units of conductance and susceptance are given as Siemens. Or in some cases, it's the inverse of ohms, often called mhos. In general, the resistance is not equal to the inverse of the conductance, and the reactance is not equal to the inverse of the susceptance, although there are some cases where it indeed works out to be that way.